and writing our programming, we stuck with the design process for our guidelines.
Our problem was to design and build a CubeSat that contained science experiments to be launched into space. The CubeSat has to fit within a 100 by 100 by 100 millimeter box and have a functioning door deployment system.
While brainstorming, we found some important information about the requirements of CubeSats. We found out that we needed solar panels to draw power to the cube. We are using these pieces of foam board to represent the solar panels. When we then thought about the actual opening of the door, we decided to use the Fisher Technic pieces and RoboPro programming to represent the door opening. After we finished the RoboPro example, we planned upon upgrading our cube with Arduino. We wanted to use Arduino because of its remote deployment feature and because it is more space conservative. Remote deployment is an attribute of Arduino that allows the cube to deploy in space while not connected to a computer.
After we knew the basic idea of what we needed to do, we reverted to the internet and did research to obtain a deeper understanding. We found images and websites that brought our NASA experience to the next level, with information such as Bob Twiggs' expenses and international knowledge of CubeSats.
Bob Twiggs is a professor at Morehead State University. He is a co-inventor of the CubeSat and assisted the design of the CricketSat, CanSat, and Pocket Phone. He has the goal to help educate undergraduate students to be able to design, build, and test CubeSats in space, which goes by the name Sputnik.
CubeSats are inexpensive because they only cost around $40,000, whereas normal satellites cost up to $5 to $50 million. This tells us that CubeSats cost prove to be economical and frugal. CubeSats are secondary payloads on rockets. This means that they take up otherwise unused space on voyages into space.
CubeSats are not just used at NASA, but around the world as well. Many small countries, including Colombia, South Africa, Romania, Vietnam, Saudi Arabia, Israel, and Denmark, are using CubeSats to gain access to space, as are universities everywhere.
We used the program Autodesk Inventor to create 9 CubeSat designs. Because of this, each group had to have one person with experience with this program. Draw the CubeSats created by 3 groups of partners.
My name is Marcus,
And my name is Jaden.
and we are Team Count Dooku. As an 8th grader, having taken a STEM class before, I knew all the ins and outs of Autodesk Inventor, while my partner did not. I helped her learn how to use the program to design our CubeSats. We collaborated and combined our ideas together to design them.
Our first CubeSat was kind of like a rough draft. One of the things wrong with it was the width of the frame X's. We messed up because we didn't realize we had to use the Pythagorean theorem to give the distance from the endpoint to the corner. Another flaw was our locking system. It extended off the CubeSat through too many millimeters, resulting in the CubeSat being too tall.
Our second CubeSat was improved. One improvement was the locking system. It is better because it fits so that the CubeSat has no extra length on the outside. And it has the diamonds inside. The diamonds are a flaw because the square in the middle does not provide nearly as much support as a triangle would. And we yet again messed up on the frame because the lines on the diamond we did not use the Pythagorean theorem with.
Our third CubeSat was a little bit better than the second. One improvement was the frame. The shape was an X with a line through the middle. This made many small triangles in every open space, which is strong and efficient. Without realizing it, we messed up the locking system again by extending it out too far, resulting in the CubeSat being too tall.
I'm Jackson.
And I'm Veda, and we're Team Darth Vader.
We decided to go with the program inventor to develop ideas for our CubeSat design. We drew 3 different designs, each with special differences. We used knowledge gained through the entire design process to pick our best design. We printed one of these in order to test our additive manufacturing.
For our first CubeSat, we wanted to be completely original. We wanted to think outside of the box. For our deployment system, we decided to use latches and springs. We were thrilled with our creative design, but it wasn't flawless. It had a very thin and frail structure, and it would not have printed well.
The very first thing we decided to improve with our second CubeSat was the structure. We made the frame much thicker to ensure support. We went so overboard in support that we put in circles, but the circles didn't serve their purpose as expected. Their printing was a miserable failure.
For our third cube, we started out with a simple design, because that's what prints best on our additive manufacturer. We decided to stick with the same launching mechanism as CubeSat 1, but instead of using switches, we are using nichrome burn wire, an easier, less complicated way. Nichrome burn wire is a form of wire that cuts through nylon, and electricity consisting of 1.6 volts runs through the wire. Even though we had a simple structure, it was too thin and feeble to perform the task at hand.
I'm Zeke.
I'm Lyle, and our team is Zach Mall. We're in a group consisting of a 6th and 7th grader. At Robertsville, only 8th graders have any experience on the Autodesk Inventor because the 7th graders are just starting to learn about it. Because of this, we are at a disadvantage.
In CubeSat 1, we liked the generic support beams because they printed well and they provided the best support. We originally wanted to have pegs on the ends to protect the solar panels. In the end, they became an external extension over 100 millimeters, which was not permitted in the design.
On CubeSat 2, we like a type of support on the bottom because it supported it while giving it more space and it printed well. No, we did not like the support on the sides because it did not print well and it was odd. We tried to make the arches to help with the extra support, but it didn't do much.
CubeSat 3 had many design flaws like the others. It had a very thin structure, which made it very frail. But we did like the support beams because they were very comparable to CubeSat 1. But unlike the others, CubeSat 3 was not completed. Because of our minimal experience with the application inventor, it took our group longer to make our first and second CubeSats.
After each group designed 3 CubeSats, we each had to pick our best design to represent our ideas towards the final cube.
We chose our third CubeSat because it exceeded all of the other CubeSats. The frame design was very efficient and sturdy, and the bars were a good width. We felt like it was our most improved out of all the others.
We chose our third CubeSat because its features were combined from our other 2 cubes. It had a good structure and an original deployment system.
We decided to put the CubeSat 1 as our representation towards our final CubeSat because it had good support beams and a functional door containment system.
Once we got our 3 CubeSats, we came together to design a cube with attributes from each group. When we printed our CubeSat prototype, we used polylactic acid, or PLA wire, which is made out of natural materials such as cornstarch, tapioca roots, and sugar cane.
During our testing of the cubes of our CubeSat, we found nothing wrong. Whereas when we looked at the extruder, we found some problems. The extruder wasn't hot enough and it was printing too fast. We simply changed the heat from 215 degrees Celsius to 225 degrees Celsius and we slowed down the printing speed.
After the extruder catastrophe, we went back and made some minor changes. These involved making the holes bigger that would contain the nylon wire, making the door thicker, and making it a more appropriate color. The biggest change that we made was using Arduino.
We wanted to use Arduino to make the door open on our cube. We intended to use the programming to heat up the burn wire and cut through the current cord.
We needed to familiarize ourselves with Arduino, so we completed some challenges.
The challenge that we chose to show you as an example is the second project, the Spaceship Interface. The program makes the lights in the breadboard alternate by touching a switch and helped us the most creating our final CubeSat program.
Once we finished physically designing the CubeSat, we communicated our results by giving this presentation to everyone here.
Here's a video and some pictures that show how our final CubeSat turned out. In the video we are using Robo pieces, but potentially we would use Arduino in our final but the Arduino could not get the burn wire hot enough, so it wouldn't cut through. We needed more amperage, not just volts.